these two.
Yeah.
So they are right here and right here.
Yeah.
I'm going to concentrate right in the middle here.
So they were able to target specific
Hawaii,
colors in the UV
a tropical island
in different
in the
swabs
Pacific
and measure the
Ocean,
amount of biological activity on
forged from
different colors that showed up
volcanoes
that
and
are visible in
teeming with
UV, but you wouldn't
diverse
see with the naked eye.
ecosystems, climates, and
It was a really great
creatures.
moment for all of us.
And for some, a laboratory for studying environments that could hold potential signs of ancient life on our neighboring planet, Mars. Four teams of scientists awake in the town of Hilo on the Big Island of Hawaii. They're not here for the beautiful beaches, the stunning waterfalls, or the lush rainforests. These astrobiologists are journeying to the volcano known as Mauna Loa to investigate lava tubes, caves formed by molten lava of past eruptions, to test a suite of instruments for future missions to Mars. After arriving near the summit, the team set out on foot across the barren lava fields towards their field site.
So this is a lava tube, which is a subterranean kind of environment. And so it's analogous potentially to sites on Mars that we've identified from orbit.
An obvious volcanism in the past. And we can see with imaging from space that there's things kind of like this skylight behind me that might be an entrance to a subterranean cavern.
And so if life potentially exists there, that would be a great place to live because it's isolated from the surface, which is very hazardous for anything to live. Here, these tubes are actually teeming with life, and so they could potentially be relevant to what we might see on Mars.
While all four teams have the same destination, they're all here for different reasons. Let's meet the teams.
My name is Dina Bauer. I am a research scientist at the University of Maryland and NASA Goddard Space Flight Center. So our role is to look at the relationships between microbes and minerals, to understand better what signatures are left behind by the microbes and the minerals, because on other planets we're more likely to see minerals as opposed to actual living microbes.
I'm Heather Graham from NASA Goddard Space Flight Center. We're actually trying to look for life by the geology itself. We're looking for mineralogical complexity on surfaces. We're also looking at elemental abundances, just the patterns and distributions of elements on those surfaces. And we're trying to use those two pieces of data to build up an energy landscape. So by looking at those minerals and those elements, we can calculate how much energy would be available for certain kinds of metabolism that microbes in these caves might use.
Over long periods of time, microbial life leaves a chemical footprint in the rocks. While it's unlikely that modern Mars has living microbes today, future missions can seek out these footprints to determine if there once was Martian life.
Yeah, so this is a really classic spectrum that you would hope to see on another planet because these are pigment peaks. So you're not necessarily getting specific in terms of species, but you can at least say there's definitely a microbe here. So we're doing a suite of measurements, a combination of what a rover would be doing and return sample analysis. Very quickly, Raman spectroscopy is a vibrational spectroscopy technique. Basically, you're firing a laser at your target, and that excites the bonds. Each mineral has its own signature because when the light hits those bonds, they excite differently and produce a spectrum. And so I use that spectra that I collect to tell me what minerals are there as well as what organics are there. So when we find them together, it kind of helps us understand their relationships. If the microbes are actually part of the precipitation of those minerals, we can infer that from looking at the Raman data. And on the flip side, if the minerals were there first and we do see signatures of the microbes, we might say that maybe those microbes are taking advantage of the elements and the energy present in those minerals.
Oh, okay, look at that. Got me some cave water. Got me some cave juice. Hey, Dina, I found water. Yeah, I'm getting your drips. We take all of these data that we're doing with field instruments and we're mapping this in a co-registered landscape of the surface. So I hate to admit that I actually learned about this technique by watching an archaeology television show, but this is a common technique that people do in caves so that they can have these co-registered maps of all of their different data types that they take for their measurements. And we're doing the same thing here.
1, so that guy right there.
And we have all of that information for all of those grids in the same place. Then we take that rock, we know each of those grid sections and all of that information about it. And then we're also taking portions of those mapped surfaces back to the lab to do measurements with much higher resolution laboratory instruments so that we can understand also not just testing the hypothesis of these patterns as a way to detect life, but also understanding if it would be possible to use a technique like this with the kind of instrumentation that we have flown on rovers and things like that.
I'm Dr. Ali Fox. I consider myself the anti-astrobiologist because I'm looking for biological patterns that are being produced by abiotic chemistry. The thing that keeps me up at night, my 3 a.m. wake-up thought, is that abiotic chemistry, so no life involved at all, can look a lot like biotic chemistry. And so when we're sending these rovers or these probes to these other planets and we have limited field instruments that we can use in those environments, we need to be really careful on how we can distinguish biosignatures. So a lot of the work that I do is trying to understand how abiotic chemistry can mimic those types of patterns. Okay, so I'm going to be going right there. That's good. So I'm doing a combination of techniques that we can do in the field and then some techniques that we'll actually do back in our laboratory. So in the field, we're using an XRF, that's X-ray fluorescence, and that gives us an idea of what types of elements are present. So now it's switching to another beam that can actually see other types of elements. So it's adding a bunch in. So it's really helpful for me because it's not always clear from just looking at a rock that it's going to have really different mineralogy, but the difference in those elemental compositions, that tells us a lot about how that mineralogy is changing. So that's a quick, easy way for me to know that I'm getting the samples I'm interested in. And, maybe in a couple of years, once I've recovered from being outside for this much, I'll be able to come back out and collect more samples.
Understanding the chemical makeup of these rocks will bring Dr. Fox and her team one step closer to identifying true signs of life from false positives.
My name is Bethany Teeling. I am a planetary research scientist at NASA's Goddard Space Flight Center. We are trying a technique that has been often considered but not explored as much. Can we identify life using the gases that we collect from the environment?
Basically, all life breathes, and life gives a particular signature of CO2 versus geological processes. So we can come down here and we can make a bunch of measurements of the ambient area and back in little crevices and get an idea of whether there is life in the crevices or whether this is just ambient CO2.
One of the things we recognize is that it's a lot easier to sample gases. I mean, if you think about it, if you have to take one of these rocks around here, you have to crush it up and probably put it in acid and do a lot of stuff, a lot of chemistry before you can actually analyze it. With the gas, you can send it directly into an instrument and get hopefully some results. So we're trying something new here. We're trying to figure out if you can use the isotopes of carbon dioxide and methane to see if we can identify the life that we know is already here. So we've come up with a few unique and very new sampling strategies. One that I think is very fun is called the lasso technique. So we have this incredibly long tube. I have gotten pretty good over the past few days at lassoing. I'll take a few coils in one hand and throw it into the back of an alcove, go back there and breathe. So this is one technique where I can stay back, turn my head, and just